Right now in Shanghai, a factory is producing jet fuel using nothing but air and water. No oil fields, no drilling platforms, no massive tankers unloading at ports. Just advanced systems capturing carbon dioxide straight from the atmosphere, combining it with hydrogen generated by splitting water with solar energy, and creating fuel chemically identical to what powers commercial aircraft engines today. The engines can't tell the difference. The molecular structure matches traditional jet fuel exactly, except no fossil resources were extracted, transported, or burned in the process. The company behind it is called Carbonology. Their facility opened in January 2026 in Shanghai's Lingang area. What makes this even harder to grasp is that this represents just one of 6 major breakthroughs China is advancing simultaneously. 6 active technologies, each addressing a different part of the same enormous challenge. And if turning air into jet fuel sounds remarkable, wait until you hear about the other 5. If you enjoy these kinds of forward-looking stories, give this video a like and subscribe so you catch what's coming next. By the end, you'll see exactly what puzzle these innovations are solving, why cracking it could reshape global influence in ways most people haven't considered, and how the world of 2035 will look dramatically different from the one powered by traditional oil. To appreciate why these developments carry such weight, we first need to understand the core issue they aim to fix. The vulnerability few discuss openly. China stands as the world's second-largest economy. Its manufacturing sector produces a vast portion of global goods. Its cities have expanded at unprecedented speed. Yet all this progress has depended on energy supplies the country doesn't fully control. Over 70% of China's oil comes from overseas sources across the Middle East, Africa, and Russia. That level of reliance is significant on its own. The deeper concern isn't just the source countries. It's the route those supplies must take. Every barrel travels by sea on tankers, and nearly all of them pass through one critical choke point, the narrow Strait of Malacca between Malaysia and Indonesia. At its narrowest, its passage is less than 3 kilometers wide. It functions less like a busy shipping route and more like a strategic bottleneck that an entire economy must navigate daily. Roughly a quarter of global traded oil flows through this strait on any given day. For China, the proportion is even higher. If that corridor were ever disrupted by conflict, accident, or deliberate closure, Chinese factories wouldn't just slow down. Supply chains would grind to a halt, prices would surge, and economic impacts would hit almost instantly. Strategists have a term for this exposure: the Malacca dilemma. China has never controlled this waterway, and in a crisis, others could effectively press pause on the world's second biggest economy. For decades, China has worked to reduce this risk through pipelines across Central Asia, port investments in Pakistan and Myanmar, and strategic petroleum reserves. But these remain temporary fixes. The oil still has to cross oceans first. The fundamental weakness persisted. What would truly resolve it isn't a new pipeline or larger stockpile. It's energy that doesn't need to be transported at all. Energy produced locally from resources that exist everywhere. That's exactly what Carbonology has begun to deliver, making fuel from thin air. Consider this question. What if jet fuel could be created the way plants produce energy? Not from ancient underground deposits, but from elements already present in the air around us. That's the breakthrough Carbonology has achieved. The process is more straightforward than it sounds when broken down. It begins with direct air capture systems that pull carbon dioxide from the atmosphere. Next comes electrolysis, which uses renewable electricity to split water into oxygen and hydrogen. The captured CO2 is then combined with that hydrogen under controlled conditions. The molecules rearrange into synthetic liquid fuel. The result is chemically indistinguishable from conventional jet fuel refined from crude oil. Aircraft engines run on it without modification. Airlines have already signed agreements to purchase it. The European Union has mandated that a growing percentage of aviation fuel come from sustainable sources, starting at 2% now and rising sharply by 2050. This creates built-in demand even before the fuel reaches full cost parity. Carbonology started with a small 100-ton pilot line. They're scaling to 1,000 tons, then 5,000 tons, with plans for a full commercial plant targeting 100,000 tons annually by 2027. Major investors, including Sequoia China and regional funds, have backed the project. When experienced energy investors commit capital after thorough review, it signals strong technical and commercial potential. But producing fuel is only one part of the broader energy transition. Even with fuel available anywhere, another major challenge remains: storing energy when the sun isn't shining or wind isn't blowing. Storing sunlight in frozen air. Solar and wind power face a fundamental timing issue. Generation doesn't always match demand. Batteries help, but even the largest lithium installations typically provide only 4 to 5 hours of backup. That falls short for long winter nights, extended cloudy periods, or continuous industrial operations. In late 2025, China activated a different kind of storage system in the Gobi Desert. The concept is elegantly simple. They liquefy air. Ordinary ambient air is cooled to around 194 degrees Celsius until it becomes a liquid. This liquid air is stored in insulated tanks, holding its energy potential like a charged battery. When power is needed, the liquid is allowed to warm and expand dramatically, up to 750 times its liquid volume. That controlled expansion drives turbines connected to generators, releasing electricity back into the grid. Paired with a 250-megawatt solar farm, excess daytime solar power is used to create the liquid air instead of being curtailed. At night or during low generation periods, the system delivers steady power for up to 10 hours. That's more than double what most large battery systems currently achieve. Importantly, it requires no lithium, cobalt, or other critical minerals, just air, advanced cooling technology, and standard industrial equipment. The plant generates around 180 gigawatt-hours annually and has operated reliably since startup. This addresses electricity storage. But heavy industries like shipping, chemicals, and steel still need storable, transportable fuels, the molecule that could transform everything. Ammonia is familiar to most people as a common cleaning agent with a strong smell. Few realize it could become one of the most important energy carriers of the coming decades. Hydrogen burns cleanly, producing only water. However, transporting pure hydrogen is extremely difficult and expensive due to its low density. Ammonia solves this by binding hydrogen into a stable liquid that's far easier to ship and store. At the destination, the hydrogen can be extracted. In essence, ammonia acts as a practical vehicle for moving clean energy across oceans. Traditional ammonia production is energy-intensive and relies heavily on natural gas. But in Shaanxi province, a new solar-powered plant is operating at 100-ton scale. It produces ammonia at room temperature using nitrogen from the air and hydrogen from water, achieving over 90% efficiency across more than 1,200 continuous hours. The applications extend far beyond fertilizer. Ammonia can power large ships directly, with Japan and South Korea already testing ammonia-fueled vessels at sea. Since shipping carries about 90% of global trade, shifting this sector away from oil would be transformative. The connecting thread: hydrogen. Look closer and you'll see hydrogen links every one of these advances. Synthetic jet fuel requires hydrogen to combine with captured CO2. Liquid air storage benefits from abundant clean electricity, often used to produce hydrogen. Solar ammonia production centers on hydrogen as its key building block. Hydrogen serves as the essential currency enabling the entire clean energy ecosystem. China's green hydrogen output grew from around 23,000 tons per year in 2019 to 125,000 tons by 2024. Guangdong province alone is developing an offshore wind project targeting 80,000 tons annually. China now produces 65% of the world's electrolyzers, the critical machines that convert electricity and water into hydrogen. National policy has elevated hydrogen to the same strategic level as oil and gas, with ambitious price targets and substantial investment. Traditional oil transport involves complex global supply chains vulnerable to disruption. Hydrogen produced locally from air and water offers a supply chain that can be contained within single facilities, with costs that continue to decline. Even major traditional energy companies are adapting. One of China's largest oil refiners saw profits fall 37% in 2025 and responded by converting facilities to produce sustainable aviation fuel. The final piece, fusion energy. All these technologies still rely on consistent clean electricity. The ultimate solution could be fusion, the process powering the sun. In fusion, light atoms combine at extreme temperatures, releasing massive energy with minimal waste and abundant fuel from water. China's East Tokamak reactor achieved record plasma stability in 2026, holding conditions longer than previous attempts. While commercial fusion remains years away, China is investing heavily. When paired with abundant fusion power, synthetic fuel production, hydrogen generation, liquid air storage, and ammonia synthesis all become dramatically more scalable and affordable. Together, these form the foundation of a closed-loop energy system. Inputs are air, water, and electricity. Outputs include fuel, power, chemicals, and fertilizer. No mining of finite resources. No dependence on distant geology or vulnerable shipping routes. The bigger strategic shift. For over a century, energy power came from controlling oil deposits and the routes they traveled. Those choke points created leverage. But if energy can be manufactured locally from ubiquitous resources, geography loses its strategic dominance. Influence shifts to those who build and export the enabling technologies. China already dominates solar panel manufacturing and electrolyzer production. It is exporting the infrastructure of the new energy era, much like oil nations once exported crude. Over 1 billion gallons of new renewable fuel capacity is entering production pipelines this year. Refineries are being repurposed. These aren't future projections. Construction is underway now. The oil-based world didn't formally end. It simply began losing ground to systems that are faster, cleaner, and far harder to interrupt. One facility, one technology, one country at a time. If this gave you new perspectives on where energy is heading, drop a like, subscribe, and enable notifications. The next video will connect even more dots most people haven't seen yet. Final question for the comments. If energy can be produced anywhere from air and water, which country do you think faces the biggest adjustment? Share your thoughts below.